Hey guys, this video is going to be about pH and pOH scales. And so like calculating the pH, calculating the pOH, concentration of H, concentration of OH, and the real difference between strong acids and weak acids and strong bases and weak bases. All right, so to remind you, over here on the right is a pH scale, and I've added pH and pOH and hydroxide and hydrogen as well, so that you can see the relationship here between these. So down here at the very bottom, that's where it's the most acidic. So the stronger acids are going to be all down here if it's somewhat concentrated, or more concentrated than a very, very dilute solution. Up here is the basic solutions. So down here at pH 0, you can see that the concentration of hydrogen is just 1, and the concentration of hydroxide is 1 times 10 to the negative 14, and the pOH is 14. So always the pH and the pOH here are adding together to give you 14 all the way across. Okay, so pure water is here at 7, and then we have sodium hydroxide, 0.1 molar sodium hydroxide has a pH of 13 and a pOH of 1. And since this is basic, we have a much, much higher concentration of hydroxide than we have of hydrogen ion. And down here where it's acidic, the hydrogen ion is bigger. Now at pH 7, these two are equal to each other because it's neutral, and so you have equal amounts of both of them. And here are the equations that you need to remember. I'm pretty sure they're on the formula chart, but just in case, you might want to write them down. You should remember them. It was a fairly memorable unit in sophomore chemistry, but pH is equal to the negative log of the concentration of H, and then this is the reverse of that equation. So if I have the pH equation, and let's say I'm given pH and I want to find hydrogen, first I would have to get rid of the negative sign, so multiply by -1 on both sides or divide by -1, whichever one you want. So I have negative pH is equal to the log of the concentration of H, and you can't divide by log. You have to undo a log by using its base, and this is log base 10, so I'm going to take 10 to the log of H, and then I have to do the same thing on the other side, and so that's where this equation right here comes from. It's the opposite of this equation. Same here with this one, it's the opposite of this equation. And then we add the pH plus the pOH together to give us 14, and that comes from this equation that we went over in the previous video. And it's simply just taking the negative log of both sides. You end up getting this, and I can show you in class if you want to see how that's derived. You don't have to know how it's derived, but that's where it comes from. All right, and then the significant figures, so the number of decimal places in the log is equal to the number of significant figures in the original number. So what that means is that when you take the logarithm of a number, the significant figures is only in the decimal places. And when I do examples, you'll see what I'm talking about. All right, so we're going to find the missing values of pH, pOH, hydrogen ion, and hydroxide ion for the following solutions and determine if the solution is acidic or basic. So I'm just going to, up here at the top, I'm going to write down the equations really quick so that you can see them while they're on the screen, and I can point to the ones that I'm using. And these are the only ones that I really use. I don't use the 1 times 10 to the negative 14 all that much unless I am doing a different calculation, which will come much later. All right, so I'm going to make kind of a little table. It helps me keep track of what I've found and make sure that I find everything that I'm supposed to find. All right, so I'm going to change the color. Okay, so I have 1 times 10 to the negative third, and that concentration is hydrogen ion. First, that's this. I'm just going to fill it in. All right, and then if I want to find, I'm going to find the pH first. So I'm going to plug that number into this and plug it into my calculator. So negative log of 1.25 times 10 to the negative third would give me 2.903 as the pH. So this has 1, 2, 3 significant figures in it, so I should have 3 decimal places for sig figs. It's really not that important as long as you're within plus or minus 1 significant figure. but just in case, that's how you do it. All right, and then for the pOH, it's really easy. Oh, I forgot to write that equation down. So the pH plus the pOH over here on the left is equal to 14. So that's really easy because I've got 2.903 for my pH, and so it'd be 11.097 for my pOH. So those two always add together to give you 14, right? Okay, and then for my OH, I'm going to use the pOH. I'm going to use this one. So I'm just going to stick 10 to the negative pOH, so 10 to the negative 11.097, and that would give me 8.00 times 10 to the negative 12. I would really strongly encourage you to try to put a couple of these in to make sure that you're putting them in the calculator correctly before you do an actual assignment. Just try it with a couple of these. Remember that you need to use E when you type in times 10 to the negative 12, the capital E. And also remember that this button right here is the second log button on a calculator. So if you have log, then that's 10 to the, and it has a little caret on it, or hat, or whatever you call it. So B has a pH of 9.46. So I'm going to go ahead and put that over here. And so my pOH is going to be 4.54. And then I'm going to calculate my hydrogen ion by using this equation over here on the right side. I'm going to plug in my pH right here to get out my hydrogen concentration. So 10 to the negative pH is equal to 3.5 times 10 to the negative 10. All right, and then for my hydroxide concentration, I'm going to do the same thing, only I'm going to use my pOH. So 10 to the negative pOH, use this equation, right? 10 to the negative pOH is going to give me 2.9 times 10 to the negative fifth. And if you'll notice, this had 2 places behind the decimal, and they were the pHs, and so this is only going to have 2 digits in it for significant figures. And then next, I have 4.5 times 10 to the negative 10th molar hydroxide. And so I'm going to find the pOH first. I'm just going to plug in my hydroxide into that equation, negative log of this, and I will end up getting 9.347. Again, this one has 3 digits, and so for the logarithms, you should have 3 digits after the decimal. All right, and then if I subtract that from 14, I get 4.653. All right, and then I'm going to take this value, the pH here, and I'm going to plug it in right here and get the hydrogen ion concentration. And so that's going to be 2.22 times 10 to the negative fifth. All right, now I want to let you know that if you don't use the rounded numbers and you are using this equation to go between hydrogen and hydroxide, there's going to be a little bit of rounding difference, and that's okay. All right, so the pOH here is 11.302, and so my pH is going to be 2.698 because they have to add together to give 14. And then to get the hydrogen ion concentration, remember I'm just going to take 10 to the negative 2.698, and that is going to give me 2.00 times 10 to the third, negative third, I'm sorry. And then for the hydroxide concentration, I'm going to use this one, same thing, 10 to the negative 11.302, right here at the top. And that would end up giving me 4.99 times 10 to the negative 12. And so what it asked us to do was calculate these values and determine if the solution is acidic or basic. So I'm just going to look at the pHs. If it's below 7, it's acidic, and if it's above 7, then it's basic. So looking at these, this is below 7, so this is acidic solution, and then above 7, so it's basic. Again, this is below 7, so it's acidic, and then below, so it's acidic. So 3 acidic solutions and then 1 basic solution. All right, so what makes an acid strong? It's the ability to lose hydrogen. So if an acid loses its hydrogen very, very easily, then it's a strong acid. And if it keeps most of its hydrogen, so the anion keeps the hydrogen intact and doesn't release it, then it's going to be weak. And there's several different factors that cause the anion to hold on to the hydrogen ion, but one of them is electronegativity, right? So electronegativity is an atom's ability to pull the electron density closer to itself and hog all the electrons in the bond instead of sharing it equally with the other atom. And so fluorine is the most electronegative element on the table right here. And it's really, really small. And so hydrogen and fluorine can get really, really close together. And so hydrogen doesn't leave very easily. So that's why hydrofluoric acid is weak when all the other acids from this group are strong acids. And they actually increase going down. And that's because these atoms down here are getting so much bigger. So these are much smaller. And then fluorine's really, really tiny, because the atomic radius increases going down and to the left if you don't remember. So bigger atoms go down the groups. So the bigger the atom is that hydrogen is bonded to, the further away from the atom it is. And so this bond length is longer. And not only that, but these are less electronegative. So this is Hi, and this is HBr, and this is HCl. And so this red down here indicates that there's a very unequal sharing of electrons. So these electrons are pulled very tightly over to this side. They're pulled pretty tightly for chlorine too, and quite a bit for bromine, but the thing about bromine is that it's so big that it can't pull as hard as chlorine can, and it certainly can't pull anywhere as hard as fluorine can. And then iodine is massive compared to fluorine. So there's barely any dipole here at all with this, and it doesn't pull on these electrons, and it releases the hydrogen very, very, very easily, much easier than hydrobromic acid and then hydrochloric acid. And that is seen consistently going down any group that's bonded to hydrogen over here in the nonmetals. The stronger acids are going to be closer to the bottom. All right, and then for these oxyacids, so oxyacids are acids that have oxygen in it, right? So we have hypochlorous acid, hypobromous acid, and hypoiodous acid. The more electronegative the atom is, the stronger the acid gets. So it's the opposite of what's happening on the left side of the screen. And that's because this oxygen right here is really electronegative. So these guys are kind of fighting over these electrons, and so it's easily given up, and these can easily hold a charge because there's two atoms there that can easily hold that negative charge when the hydrogen is freed as H+. All right, and then down here on the bottom, the more oxygens there are, the more easily this hydrogen can take off. And so perchloric acid is the strongest of these 4 oxyacids. And guys, this really isn't all that important. I just wanted you to kind of see what makes an acid strong. All right, so what makes a weak acid stronger than another weak acid? Now, I know that sounds weird, but some weak acids are kind of strong and can really do some damage. So chlorous acid is something you probably wouldn't want to get on you. Hydrofluoric acid, you definitely wouldn't want to get on you. So increasing Ks, and so the Ka for this would be H3O plus times A minus over HA. And remember, this is the same thing as H plus. So the bigger the K, the more hydrogen it's releasing. And the more hydrogen it's releasing, the stronger the acid. So this value, the bigger the Ka is, the more it's going to release. And so just to kind of put things in perspective, if I have a 1 molar hydrochloric acid solution, the pH that we would calculate for that would be 0. But if I have a 1 molar acetic acid solution, the pH for that is going to be 2.37. So you can see the difference here. Even though the same concentration, this one is not releasing that hydrogen to give you a low pH like hydrochloric acid will. So that's the difference between a strong acid and a weak acid. Weak acids don't release many of their H pluses. And so the bigger the Ka, the more hydrogen ion it releases because it's in the products, and the less acidic it is. So the higher the pH will be. Okay, and then the same thing happens for bases. If I want to write the Kb for a base, it's hydroxide, and we'll go over all that when we start really getting into it, times the conjugate acid over the base. The larger the Kb, that means that there's more product, because if this is bigger, then that means we've got more numerator, so we have more OH. If you have more OH, it's a stronger base. So this right here, increasing strength, you don't have to be able to know that methylamine is stronger than ethylamine. What you have to know is if you're given this should say Kb, look at that. If you're given a Kb or a series of Kbs, you should be able to put them in order of increasing strength then. All right, so that's it for this video. I know it's a little bit longer than you probably wanted to watch, but hopefully you got some good information out of it.